All right, so in this video, I want to take a second. We haven't talked about this yet, and I probably should have covered it a little bit earlier. However, I forgot, so we're going to cover it now. So what we got in our last problem was we got an answer, Vy of t is equal to 2.82 sine of omega t plus some phase shift 54.38 degrees. So let's come back over here. Oh, sorry, that's not where I wanted to be. The next slide, which I've created. So this was our answer. Let me go back and get the original signal, which was Vs of t, because I want to compare and contrast these and kind of show you a new concept. Well, it's not new, but it's kind of giving a name to something we already saw, having to do with the phase shift of these two signals. Okay, so we know that if I was going to plot Vs of t, let's say Vs of t is my green waveform here, right? The one that I kind of have here already. It has no phase shift, right? We can see that the 2 pi times 5 megahertz times t, and then there's no phase shift. It would be like a +0 inside the parentheses there, and so we have no phase shift. So I would go ahead and let me just go into like a green color, and I'll say that this signal, has an amplitude of 3.3 volts, right? Well, my Vy of t, I'm going to draw that one in blue. It has a little bit smaller of an amplitude, right? 2.82, so it's going to be slightly lower, maybe something like that. Probably, not drawn great to scale, but let's just look at that for now. So that's going to be the amplitude, but also notice that my signal has a phase shift here. It has a 54.38 degree phase shift, and because it's positive, right, that actually means that that signal is going to occur 54 degrees or 54.38 degrees shifted to my reference signal, or my Vs of t. So if I were to draw this signal, it's gonna, kind of come something like this. Let's try and draw it. Let's see if I can draw it kind of accurately here. It's gonna be peaking right around here, and then it's gonna hit its trough right around there. Or maybe actually not great. I'm gonna try and draw this as accurately as I can. And then the next one would peak right around here again. I'm kind of trying my best here. I'm not a computer. Okay, so it looks something like that. So you can see that the peaks are shifted over to the left, right? The peak of my blue signal it occurs to the left of the peak of my green signal. And so this axis is almost always going to be in terms of time, right? If this was a 5 megahertz signal, so what would if my frequency here was 5 megahertz, that means that my period is 1 over 5 megahertz, which is 200 nanoseconds. Okay, 200 nanoseconds. So that means that each one of these cycles is 200 nanoseconds. And so you can see, I was talking originally about the peak, but let's actually look at the zeros of the sine wave. So there's a 0 right here on my green sine wave. It crosses 0 right at 200 nanoseconds, crosses 0 again right at 400 nanoseconds, and so on. Well, my blue signal crosses 0 a little bit earlier in time, right? It crosses a little bit earlier. It's kind of ahead in time. In terms of time, it's ahead of my green signal. So we call this a leading signal. Okay, it's important. This terminology is important because when we look at sine waves and we're talking about different sine waves, it's important sometimes to know whether or not a signal is leading or lagging another signal. Okay, so I drew this just to show you a practical example from our previous problem, what a leading sine wave looks like. It's a sine wave that occurs, its peaks and its troughs, they occur earlier in time. Basically, this peak is occurring prior to this peak in terms of time, okay? A lagging signal then is the exact opposite. So I'm gonna draw what a lagging signal would look like over here. The peak would occur somewhere here, and then the trough would occur somewhere here. Please forgive my sine waves. I'm trying my best. let's go somewhere there, and then it would come around and the peak would occur here, and then come down and somewhere there, and somewhere here. Okay, so you get the picture. So here, I'd have to draw this more like that, delete this. So now I'm looking at a lagging signal, okay? So this would be, basically the difference here is this blue signal here would basically be, let's just call it Vy of t, because that's what it is, and from my previous problem, is equal to 2.82 times the sine of omega t plus, the key here is the plus sign, plus 54.38 degrees volts. And that 54.38 degrees is, of course, with respect to this Vs of t signal, which has a phase shift of 0. So actually, let me go ahead and just write it like that. I'll just write it like this, plus 0 degrees, which is the exact same thing, right? Does nothing to the signal. Over here, if I were to call this, let's just call it Vz of t, this one would be, you know, it's roughly the same height, so I'll just say 2.82 sine of omega t minus 54.38 degrees volts. Okay, so the minus sign being the key here, and that is the difference between leading and lagging signals. Okay, so let's just again show that this is 200 nanoseconds. This is going to be at 400 nanoseconds, and we can see, we can see that my red sine wave 0 occurs later in time. Again, here it occurs later in time, so it's lagging behind the source signal, which is in green. Okay, so that right there is an important just kind of nomenclature, or we're going to use, I'll say this signal's leading or this signal's lagging by this much. You'll hear that terminology quite a bit. It's really important moving forward in this class and kind of just moving forward in electrical engineering in general. And so let me just write it at the top of the slide, leading and lagging signals. All right. And definitely keep this one in your back pocket. It's going to be important. I'm going to use this terminology from this point forward. And all you have to know is that a leading signal is one that occurs earlier in time, and a lagging signal is one that occurs later in time. And with respect to a signal with 0 phase, right, then the leading signal is the one that has a positive phase shift, and the lagging signal is one that has a negative phase shift. Okay, so I'm going to go ahead and end this video here, and then in the next video we'll get into superposition.